we've been researching for high-performance railroading using a simulation technique. It's been on the way, but this talk would like to introduce our optimization program and simulator to address it. And I begin with what the high-performance railroading is, where it would be everything that maximizes the user's profit sustainability. Everything is like production, operating time, energy consumption, parts cost, and availability, and so on. Considering all stakeholders, safety and profit, including environmental conserving and some other requirements. And a large question is that how to achieve them. We think we can contribute to it if we have a well-informed planning and control system. And that's because it can select near optimal action sequences, taking other system at the site into account by predicting our outcome of an action to maximize the profits. Of course, it's not easy, but what makes that difficult? I will explain it after introducing a problem statement. Here we formulate an optimization problem to select an optimal action sequence, taking a railroading task to fill the dump trucks at the mine or quarry. This is one of the major usage of the machine. In the loading task, the machine digs into a pile to fill the bucket and empty it onto the dump truck in the loading cycle. And the machine repeats the loading cycle until the dump truck filled up and the next dump trucks coming after that. And the loading performance depends on how the machine behaves and also the pile states. This means that if the machine does a good action to achieve a high performance, it also changes the pile shape, pile states. And at the next loading cycle, the machine takes a new action at the new states, new pile states, and the pile state might be bad for the previous good loading actions. So we need to select action sequence for not only for the immediate profit, but also for keeping a good shape for the future profit, even though the immediate profit is would not be the best. And so far, no one has been able to tackle this problem. The difficulty lies in that we need many experiments in the complex dynamics of the interaction between machine and soil. And we address the difficulty by using a virtual environment. It can make repeatable experiments systematically. And this simulation model represent dynamics of both machine and soil to observe the digging force and displacement for the realistic experiment. Typically, such a simulation model is computationally quite high cost to calculate all particle behaviors and contacts. But this simulation model is real-time capability supported by the physics engine. And roughly we can simulate roughly several thousand of loading cycles per hour. Thanks to this simulation model, in addition to the parallel computer nodes. From the next page, I will introduce the terrain and the machine model. Terrain model is a multi-scale hybrid model from author's previous work. This model effectively reduces the degree of freedom of the terrain to realize the real-time capability, but still accurate enough comparing to the typical high-dimensional DEM model. This model has can take a different kind of status of the terrain according to the situation between the bucket and the contact bodies and the terrain. At first, the resting soil is modeled as a solid and discretized in the regular 3D grid. And when the bucket comes in from terrain surface, the zone of the active soil is predicted and resolved with the particles or the variable size of mass. And the DEM is used for the particle dynamics. And the bucket experiences the active soil as a raw dimensional aggregate body with particle dynamic inertia. And it can compute resistance of contact between the bucket and the soil. And in these figures, the three different type of soil, the gravel, sand, and dirt, are parameterized by the inertial internal friction, and the retency and cohesion and mass density at the bank state. I use this type of soil at the later part of this talk. And these figures simulate each other between this and this. And machine model is a rigid multi-body systems, which can represent the effect of thrusting into a pile with driving, lifting, and tilting. Front and rear frame is connected by a revolute joint for the articulate steering. And prismatic actuator can lift up and down and dump and tilt bucket in a parallel Z-bar linkage system. And the drivetrain can transmit the revolute power from the torque curve engine to tire hub pairs via drive shaft coupled with differential gears. And these actuators are controlled by target speed and force limit. And also the machine can bound and pitching during the loading cycle because of the tire elasticity. And the tire also slip at the tire torque over resistance force. And overall, the specification roughly corresponds to Komatsu W320. And we compared the simulation to a physical experiment of a simple loading cycle like this. They agreed each other, and bucket train interaction causes soil failure and displacement reasonably. And the machine speed and digging force similar enough each other. So far, we introduced a simulator. And so far, we've not carried out the optimization I formulated yet. Instead, I would like to show the simulation ability by demonstrating the simple loading cycle. The scenario is just a forward, thrust, dig, and go back straight without steering. And we collect huge data from many experiments to analyze how the machine action and pile states affect to the performance. The machine has 8 control parameters for the driving, lifting, and tilting. And the values of the control parameters causes different machine behaviors and result in the different performances. And all values combination is counts for totally 45,000. And also, what more, we prepared 6 different kind of pile states of the different slope and different type of soil. Total 270,000 simulation to analyze it. A result as a summary, we can see the loading actions are likely to get better performance at a steeper pile, and dirt and sand looks having a better performance than the gravel. But I cannot say this clearly. So for now, I will skip about discussing this. I will only discuss about it. And each distribution plots all action performances colored by the loaded mass. And horizontal and vertical axes indicate productivity and efficiency, which means higher production per time and energy. And each edge point plot indicates best performance. And the action set is the optimal action for each pile states. Clearly, the steeper it's better. And we can see the reason of the trend at the next figure. The figure shows the bucket tip trajectory of optimal action, also showing the before and after pile shape. And at a shallow pile, the bucket needs to dig into deeper to scoop the mass with much time and energy. But unfortunately, the much soil just pushed forward and left that pile without scooped. While it tends to be easier to fill the bucket by soil failure rolling into the bucket at a steeper pile. And the histogram shows loaded mass and spread by every pile slopes. And clearly, the higher load mass at a steeper pile, good. But at the same time, the higher spread at a steeper pile, we think it's a side effect which penalizes the sequential rolling performance in some way. And the results suggest that the preferred digging action should preserve and exploit the steep pile slope, at least among the demonstration. And this means that when we set a longer scenario, which is like not just digging, but also adding other actions, the higher performance would count with the different action parameters. And also, so far, we've just watched the spread and resting pile surface. But we should consider and investigate how they penalize the sequential rolling performance. This talk, I introduced the simulator, our simulator showing the accuracy and real-time capability to explore the optimization problem. But as a next step, we will address this to investigate our optimal action sequence in practice. Thank you.